This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Which describes or relates the input impedance of a transmission line impedance pair in terms of the load impedance, characteristic impedance of a line, and the wave number, which is 2 pi on L lambda, where lambda is the wavelength on that transmission line. Now, very quickly, we also talked about, as I said, short circuits, transmission lines terminated in a short circuit. We worked out the impedance looking into this line can be written as JZ0 tan beta L, and we drew out essentially the voltage, the current, and the impedance for this particular system. And what was important was, again, just to re-emphasize that the impedance, when you're going towards a quarter wavelength, you can actually transform a short circuit to an open circuit. And essentially what we're seeing here is, as we approach, the length of line approaches lambda on 4, we get infinite impedance, and this relationship is periodic. It essentially repeats itself every lambda on 2. Okay. We did the same for an open circuit, and we found the relationship between input impedance and Z0, and we said it was cot beta Z. And I asked you to go through and spend a little bit of time actually working out the graphs to cot beta Z. I didn't draw them because that's a year 11 problem, so you guys can actually just draw what just cot beta Z is going to be. Now, the last thing that we defined was essentially a transmission coefficient, which is the amount of power which is not reflected, which is essentially the power that's actually transmitted into a medium. As we said, whenever we've got two transmission lines, cannot see. Oh, sorry. Okay. Okay. So we had these two transmission lines, and we said that when we've got two transmission lines of different characteristic impedances, or even just a transmission line connected to a load, some of the power is reflected, and we worked out gamma, and we also now defining the concept of T. And we said that because power is conserved, we know that there's a relationship between gamma and T. And from there, what we did was essentially derive this concept called insertion loss, which is related to, is similar to reflection loss. The only difference is this actually tells us or quantifies for us the amount of power that's actually transmitted in this system. Okay, that was our last lecture, right? That's just a recap of all the stuff that we did in our last lecture. Now, in this lecture, we're going to do something super exciting, right? And it's going to be more exciting than the last lecture. And the reason is, in the last lecture, we talked about transmission lines in steady state, right? And essentially what that means is somebody at some time in the infinite past has switched on a transmission line, or has charged up a transmission line, or has put a transient on that transmission line, and there is now a voltage standing wave ratio on that transmission line, right? That's what steady state analysis is essentially telling you, that everything, that a sufficient amount of time had passed, that any transients had dissipated, and the signal was essentially had no time component associated with it, right? There was only a component associated with distance, right? Now, in this part of the analysis, or in this lecture, what we're going to say is, well, what happens to these transmission lines when we actually switch on the signal, right? You know, what happens? You know, what are some of the effects that we would expect to see under those circumstances? Now, you can ask yourself, well, what are some examples of transmission lines where I'm actually switching on a signal? Can anyone give me some examples? Maybe for the RF guys, you've got a power amplifier, it's switched off, all of a sudden it switches on, right? It puts a transient on the line, all of a sudden that transient travels down that transmission line, sees a discontinuity, starts coming back, right? Reflects back from the inputs of the power amplifier, travels back forward, and all of a sudden, what's happening is the voltage on that transmission line or that antenna that you're trying to excite in order to radiate energy, well, the voltage isn't this nice sinusoid or nice square pulse that you expected. And all of a sudden that means that could cause significant issues to a receiver that's trying to receive that signal, because all of a sudden it's not what it expects, right? All of a sudden the voltage is, you know, time varying in a different manner than what it expects. Okay, the other circumstances, and we'll talk a little bit about this, is you might have a transmission line, even though that transmission line, as we said, could be relatively small because it depends on the proportion of the wavelength, could actually be a logic gate, right? So all of a sudden you switch this line from voltage 0 to voltage 1, and all of a sudden you've got something at the end of that transmission line that's going to transition from a particular logic state to another. So let's assume that it's a latch rather than a flip-flop, which is actually clocking. It's only going to measure the signal at a predefined moment in time. So essentially what's happening is that latch is going to see a time-varying voltage. Right? And we'll go through a specific example there where what we're going to do is we're going to send a pulse along a long transmission line, and then what we're going to see is various pulses on that transmission line, which you can imagine if you're looking at you've got a latch, or you've got, you know, some other gate like a NAND gate or a how do you call it, an inverter. That voltage will be the output will be time dependent. Okay. Right, so what we're going to do here in order to be able to simplify our lives is I'm going to assume that these transmission lines are lossless, right? Because otherwise the mathematics becomes too complex. And yes, it's interesting to know what happens when you have these transients on lossy transmission lines. But for the purposes of this lecture, what we're going to do is we're going to assume that they're lossless in order to be able to see what happens with these transients. So essentially what I've done is, if you remember, I've made the R component equal to 0. Usually you've got R, I plus L di dt, which were the transmission line equations, and di dz was equal to GV minus CdV dt. And the R and the G were actually the loss components. So essentially, I've said the line's lossless. I've now had this set of coupled differential equations, which are really simple to solve. And here, what I'm going to do is, again, if I was differentiating, doing the trick that I did in the last lecture, where I differentiated both of these, the left-hand side with respect to Z, and I can actually use that in order to be able to come up with these second-order differential equations, which are uncoupled. Then I can say, well, let me now write what I expect the voltage with respect to distance and time to be. And what I'll do here is, because we're going to be looking at voltages, arbitrary solutions, I'm not going to assume that we've actually got a particular form of the for the solution of these equations, other than to say, well, there's a positive going wave and a negative going wave, and there's also the current, where we're going to leave the V positive going wave and V negative going wave to be unknown arbitrary functions, but we know what their argument is going to be in order for them to be able to satisfy these differential equations. And as I said, we're not assuming sinusoidal excitation, and essentially the system we're trying to deal with is the following. So we've got a signal generator or a source. It has a voltage, it has a source resistance, we've got a transmission line, we've got a load, and at some time t, and in this particular case we're going to assume that the switch is closed at t equals 0. So we've got this system, it's sitting there, and all of a sudden somebody's going to come past and flick the switch. Right? And we want to see what's actually happening for this system. Okay, so as we said, you know, one of our friends walks past, or one of our colleagues, and you know, at time t equals 0, you know, they close the switch. Now we've got to start working out what we expect the voltage is going to be on that line, right? Now, the thing that's important here is that in order to be able to start looking at solving this problem, we have to appreciate that information, voltage signals, etc., travel at a finite speed. And we've been told, at least by Einstein, that no signal can travel faster than the speed of light. So all we're saying is, at some time t, we're going to close this switch, and as far as the system's concerned, the only thing that it knows is, hey, the source is connected to this characteristic impedance. It doesn't know anything about the load at the moment. All right, is that what you're going to say? Okay, good. So it doesn't know anything about what's happening at the load. So essentially, when we're working out what the amplitude of that initial voltage wave, the only thing that we can say is we've got the source resistance here, we've got the voltage source, we've got the source resistance, or the resistance of the generator, and the characteristic impedance of that line. That's the only thing it knows. It hasn't, not enough time has progressed for the system to actually know that there is a load somewhere in the distance, right? So this is the thing. The initial amount of voltage which comes out of this interface is essentially calculated by using this voltage divider, but essentially the voltage is related to the characteristic impedance of the line that is connected up to that source. Okay? Is that clear for everyone? So why doesn't it know about the load impedance? Right, in DC, when you're doing your first year calculations, right, when you're first learning about how do you call it? What is it? Your basic circuits, right? You go G, and suppose you had Z naught, or in this particular case, you would go ZL, and you'd work out the voltage here that would take into account all three components. Why am I saying to you, why am I indicating here that, hey, the only thing that happens if you've got a transmission line, at the very instant that you close that transmission line, the only thing that you know is about Z naught. Yes?
Because the current has enough time to travel up to the load at the end.
Yeah, so it doesn't know anything about the load. That's right. Nobody's told it about it. It doesn't know anything. It just knows, hey, I'm connected up to this characteristic impedance. Now, I've done something a little bit naughty here, and hopefully it hasn't confused you. If you were calculating this in first year, you don't include the characteristic impedance of the line when you're doing these calculations, right? Usually what you would say is RGZL, right? Because Z naught, the characteristic impedance of the line, you assume you neglect that doesn't enter into the equation, right? Here I was just trying to make a point. But when you're doing these calculations, at least for transmission lines, the only thing that you know when you first flick the switch is essentially my source is connected to a line and it has a particular characteristic impedance. And there, what you're able to do is use Kirchhoff's voltage law, which is essentially the voltage around any closed loop is equal to 0, and from there you can actually work out, no surprises, what your initial positive going voltage wave is going to be, and of course, likewise, you can also work out what your positive going current wave is going to be. Question. That's what you expect it to be at time 0. What do you expect the voltage to be at time infinity? Across this load. Yes.
There you go. The voltage divider between the loads and
That's it. Right. So here, perfect. What you've got is you switch off the you switch on the load. Sorry, it shouldn't be. I've drawn the wrong point. Let me draw it again. So when you first start off, right, and you close the switch, what's going to happen here is you're going to get a voltage and current wave, and you're going to initially consider the voltage here to be the voltage divider where you assume the load's Z0, and at time infinity, what's going to happen, after all the transients have died down, you're going to get that. Okay? All right. So so the point is, you switch on you initially switch the switch in this particular case, and remember, the thing that I also need to point out, which I probably didn't mention, which I should have, is these transmission lines are uncharged. They're at quiescent conditions, which essentially, what I'm saying is the voltage and current are actually both equal to 0. Okay?
Excuse me?
Yes?
Yeah, so just at time infinity, do we not consider the impedance of the transition line level?
No.
Okay.
And that's why so it tends to your first year circuit theory.
Okay.
Right? Because all of a sudden that transmission line, that characteristic impedance is, it's not, that's just, it stops that wave from being able to, propagate. But after a sufficiently long time, you neglect that. Okay. So now let's continue. So we said essentially we had the circuit, we closed the switch, right? We closed the switch. We set up our initial, our what's going to happen at time equals 0, and we've got our first positive going voltage and current waves, and we've worked out what the voltages and currents are going to be. And essentially, depending on the length of the line, this wave is now going to hit this transmission line. Okay. This, yeah, but it washes out. I think this is, I'm going to complain to the university, this is discrimination against old people. Okay. All right. So we've got the transmission line here. The voltage wave is travelling along this transmission line until it actually hits this load, right? So it hits this load, And we say that it's going to hit this load after some time t, which is essentially the length of the transmission line divided by the velocity of electromagnetic waves in this transmission line. So let's look at what happens at this load, right? So we know essentially that we've got a voltage and current wave. We've got a voltage and current wave here. And when we look at the load, we would expect, and we know that the voltage and current wave, you know, are related to this characteristic impedance Z naught. But at the load, what happens is essentially this condition is no longer satisfied. Okay? So something has to happen. So the question is, how is that inconsistency resolved? Right? Can anyone guess? I mean, you can actually see here, but anyway. How's that inconsistency resolved, right? Because all of a sudden, what I'm saying is this voltage wave has now hit this load, right? And all of a sudden, you can say to me, one or two things happen. A, Ohm's law doesn't hold anymore, and I'm going to say BS, it does, right? But just say, or something else has to happen. Now, let's assume that Ohm's law, you know, holds under all circumstances. So what will need to happen? Well, we need to generate a reflected wave in order to be able to meet those boundary conditions. Okay? And essentially, what we're saying is, in order to meet these boundary conditions, a negative going voltage wave needs to be generated. And if we use, we rewrite Ohm's law in terms of, you know, the total voltage, the forward and the negative going voltage, and the positive and negative going current. And remember, there's a negative sign here because of, and then the negative becomes positive. We are now able to work out what the reflection coefficient is, right? And essentially that tells us what the magnitude and phase of that reflected wave is going to be in terms of the load impedance in Z naught. No different to what we did in our steady state analysis. Here I'm just explaining to you why that happens and what happens at that particular instant when the positive going wave actually hits that discontinuity. Now, there's an issue, right, which is all of a sudden this wave that hit and was reflected back from the load, all of a sudden that's going to move forward and it's going to be travelling along this transmission line until it hits the source, right? Now, the source, there's no reason why the source impedance and the characteristic impedance of a line have to be equal. Usually we try to choose them to be equal, but they don't have to be. If they're not equal, we get another transient. All of a sudden we get the whole situation that we described with the load happening again at the generator. So all of a sudden then what we've got is some of the signals going to be transmitted and absorbed into the generator. Some of it's going to be reflected again at that interface and go back towards the load. Right? Now, if both situations were lossless, what will happen is we would have that wave, that pulse, or that wave going back and forward and back and forward and back and forward. But generally what happens is that, you know, some of it's absorbed in the lobe. The magnitude of gamma isn't always equal to 1, right? So therefore, that usually helps absorb and reduce or attenuate that signal going backwards and forwards on that particular transmission line. Okay, so let's do an example. Okay, and this is the example. Okay, suppose I've got a generator, and this generator, for argument's sake, is a DC generator, and its signal that it generates, or the voltage that it puts out, is 100 volts. And for whatever reason, you know, design, you know, you know, I mean, I'm notorious for breaking connectors, so I've got into a connector and I've broken a connector, and all of a sudden the impedance is now 40 ohms. And let's assume that this generator is now connected to a transmission line which has a characteristic impedance of 60 ohms, which is then connected to a 120 ohm load. All right? So what we want to do is calculate the voltage and the current at the source, halfway down the line at the load. Right? So we want to work these variables, or these quantities out at these locations as a function of time. Okay. So the first thing that we said was, remember that in order to work out the initial positive going voltage wave, what we had was we were going to neglect what's happening at the load, and it's really a voltage divider where we're looking at the source impedance of the impedance of the source and the impedance of the transmission line, right? And from that, what we do is we were able to calculate the voltage at this interface here, right? When it's just a simple voltage divider, we said it's 100 volts. The source, we know that this is 60 ohms. So therefore, the voltage here is essentially 60 volts, right? Because, you know, just think of it that way, right? 60 plus 40 is 100, you know. Sorry guys, my apologies. All right, so you can actually work out what the voltage is, and likewise, if you know what the voltage is at this particular location, you can actually work out the current. Okay, now what we're going to do is actually calculate the voltage reflection coefficient of the load. All right, and we've gone through this analysis numerous times, and we said that the voltage reflection coefficient is the load impedance minus the characteristic impedance of the line that's connecting to it, 100, and the sum of the characteristic impedance plus the load impedance. So this gives us a reflection coefficient of positive 1/3, right? Which means that the positive and the negative reflected voltage are in phase. It's just that their amplitude, the amplitude is only 1/3 of the reflected, the magnitude of the reflected voltage wave is 1/3 the magnitude of the positive going wave. And likewise, we can do the same calculation for the source reflection coefficient, and we find out that that is minus 1/5. Now, we've gone through this specifically so that I've got a positive and a negative going coefficient, right? And I've done this specifically in order to be able to illustrate what happens when you've got a positive and negative going coefficient. Okay, so what we're going to do is we're going to draw our bounce diagram, or our voltage current bounce diagrams, right? So in this particular example, I stated to you all that the length of the transmission line was of such length that it takes 1 microsecond for a signal to go from one end of a line to the other, right? So you can see it's a very long transmission line, right? Electrically a very long transmission line. So what we do is we're going to start drawing our bounce diagrams, right? So usually the way that we do our bounce diagrams is we draw two parallel vertical lines, and what we've got is we draw the voltage going from that, you know, at time 0, which is the excitation, the initial voltage, traveling towards the load, is reflected at, you know, time 1 equals 1 microsecond, or you can actually just put here, you can actually put it as one microsecond as I've done, or you can just put it as tau, where tau is the time that it takes to go across that transmission line. Now, what have we said? Well, we've said that the reflection coefficient, right, for the transmission line, so the transmission line load is 1/3, right? So therefore, if the initial voltage is 60 volts, the reflected voltage is going to be 20 volts, right? Now let's continue this, right? So therefore, we've got the, voltage wave has hit the load, it is reflected, right? Now, can anyone tell me what they think the voltage at this point is going to be? 80. You're right, because they're both positive. Okay? Good. All right, so what happens here is we now have the signal that is reflected, and it travels, it hits the source, right? Just before it hits the source, we expect this voltage to be 80, right? But we know that the reflection coefficient for the line to the generator is -1/5. So therefore, the reflected voltage is going to be -4 volts. So the voltage is going to be 80 minus 4, so it's going to be 76 volts here, right? So what we can do is we can actually start drawing these diagrams. Sorry, we can actually start drawing these diagrams where if we're at the source, we're at some other location or midline between the source and the load, or at the load, we can actually start working out and determining what these voltage waveforms are going to look like. All right, and essentially all I'm doing is saying, well, if I'm at the load, it takes t, where it's L1 Vp, or 1 microsecond, in order for the voltage to get there. And before that, the voltage is 0. Once the voltage wave gets there, it's 80 volts. And until we get we have this reflection, the reflection from the load back to the source, and it hits us at the load, that voltage is going to remain at 80 volts until we get that reflection, which makes the voltage go down a little bit, right? And likewise, when you're at the source, your voltage is 60 volts here. Remember, you get the -4 volts occurring here, so it goes from 60, sorry, that was 80, -4 is -76. And then you have another reflection, you've got the -4/3 plus the 4/15. So therefore your resulting voltage is 1124 on 15. Right, so this gives you essentially what you would, the waveforms that you would expect on this transmission line system as a function of time. Right, and eventually what you'll see is that it tends to, or in infinite, as time goes to infinity, it attains its steady state voltage. Okay. All right. Now that was a pretty simple example, right? Because what we did is we said the transmission line was, quiescent, and what we did is we switched on the voltage, and the voltage was from the source generator was going to be a constant value. Now the question, however, is, well, what happens when you're no longer exciting it with a constant voltage output, or the generator is not generating a constant voltage output, but instead it's putting a pulse on the line, right? So therefore, all of a sudden it's going to produce a blip, right? So essentially what I'm saying is, hey, I'm going to close this switch, right? Or you can actually say, I'm going to close and open that switch, and this is constant, or no, that's not the appropriate thing to say. Okay, you can say that this is connected, and all of a sudden this is going to generate a pulse. And the duration of this pulse is 1 microsecond, and the time that it takes, in this particular example, the pulse to go from one end of the transmission line to the end, or to the load's 1 microsecond. This is just another example, but specifically what I'm trying to illustrate here is what happens when you'd have these pulse sources rather than these constant voltage sources. It adds this extra layer of complexity. Okay, so essentially what we've got is we're drawing the bounce diagram again. Okay, we've got the voltage as we expect, but now we've also got a time component, right? Because what we know is by the time the signal actually hits the source, not the source, the load, the voltage at the generator goes to zero in this particular case, right? So the generator gets switched off. I'm generating a pulse, right? That's the situation I'm trying to deal with. So therefore, that's why I'm showing that this pulse, which has a duration of 1 microsecond, is actually traveling across. So what happens is you've got for the as far as the source is the load's concerned, there's nothing for 1 microsecond. After that, you have the signal hits, but you've also got, at the same time, you get a reflected wave. So essentially, for the next 1 microsecond, at the load, you're getting 80 volts, right? Now, you've got the signal that's reflected. Now, what happens at the source? Well, now you've got 80 volts hitting the source after some period of time, essentially after the second bounce, but you've also got the minus 4 volts due to the reflection coefficient. So all of a sudden you're getting minus 76 volts, but you're only getting that for a... I'm making a mistake here. Sorry. Okay. I shouldn't have added. Okay, so I've got 60, I've got 20. There's nothing anymore at the source. Sorry. So therefore it was 20 plus the minus 4 gives us minus 16. Okay, that's my bad. Sorry, what I assumed when I was describing it, I assumed that the voltage generator still had a voltage on it. That's not true. The time it takes at least 1 microsecond to get back. So as a consequence, there's nothing there, right? The voltage generator has actually switched off. So the only thing that this interface sees is the 20 volts that's being reflected back, plus the minus 4 volts, which is required in order to meet that boundary condition. So the voltage at this interface is going to be minus 16 volts, right? With minus 4 volts coming back. So the minus 4 volts is going to hit this interface, right? When we know that there's a reflection coefficient of 1/3, so therefore we can actually work out that what the voltage is going to be at this location, and so on. So essentially, if you go through the analysis, what you're able to convince yourselves of is that at the source, initially you got for 1 microsecond, you've got 60 volts. There's nothing after that for the next 1 microsecond. You now get the reflected signal coming back at you, but you need to also meet the boundary conditions. So therefore, instead of 20 volts, you get a 4 volt reflected wave. So therefore, the voltage at the source is 16 volts, and that situation continues. And what happens is for the 4th to 5th microseconds, you get a return voltage of minus 16, or you get a voltage of minus 16 on 15. At the load, what you see is, if you go through the calculations, you've got an initial 80 volt positive going pulse. You now have a pulse which is minus 16 on 3, for between 3 to 4 microseconds, and between 5 to 6 microseconds, you've got a pulse which is of magnitude of 16 on 45. And halfway between the line, essentially the voltage that you see is this relatively complex waveform, right, where you've got between half a microsecond to 1.5 microseconds, you've got 60 volts. From 1.5 to 2.5 microseconds, you've got 20 volts. From 2.5 to 3.5, you've got minus 4 volts. 3.5 to 4.5, minus 4/3. 4.5 to 5.5, 4/15. right? So you see that you start getting this complex transient type behavior on that transmission line, right? So therefore, even though the transmission line, you've sent a pulse, all of a sudden, at your load, if you were sensing your load, for example, if you had something there that was, a gauge or something, this is the voltage that you would see. So you'd see a positive, negative going voltage, even though we've only applied a positive going voltage onto this transmission line, right? And likewise, if you were sensing, for whatever reason, midway between the transmission line, a little bit more, okay, you would see a voltage versus time relationship which would go from 60 to 20 to negative to positive to negative to positive, right? Eventually dying out, but you can actually start seeing that the pattern is relatively complex. So therefore, it's interesting, right? Because all of a sudden, if you now switch, if you've got a gate and you're using it to feed a transmission line, all of a sudden you can have a positive or negative going voltage. And, for example, if you had, as an example, a CMOS circuit and all of a sudden your gate goes below your ground, you can start getting some interesting effects, right? You can start having latch up and you can start having a whole bunch of interesting effects, right? So this is the reason, so other than this being something really exciting and interesting mathematically, it's interesting because it has effects on how you design certain things, but also it tells you that there are certain circumstances where, and specifically in certain processes, that things can start going wrong, and you need to be aware of what you're connecting your load through a transmission line. What are the potential effects that can occur under those circumstances? Okay, exciting? No? Yes? All right. We're going to continue. All right. So far, what have we done? Well, we've done steady state analysis, we've done some transient analysis, and with the transient analysis specifically, we started off with uncharged transmission lines, or transmission lines which there was no voltage and current travelling on them, right? Or they were completely uncharged, right? Or you can think of circumstances where all of a sudden you might have you might have a logic circuit that all of a sudden it's feeding a transmission line and it's kept at a particular voltage, right? So you've got a transmission line, the gate is high, or the output is high, so all of a sudden you've got a particular voltage and current on that line. Okay? So what we want to do is understand what happens under those circumstances and how would we analyze that particular complex system. Right? So, just to reiterate, so far I've been kind to you and I've said, well, I started off with sinusoidal analysis and I said, let's make it really easy. Then we said, well, we're going to do transient analysis, and let's assume for this transient analysis everything was zero. Now I'm going to say to you, well, guess what? We're going to start dealing with more complex problems, and that is where these transmission lines and systems have non-zero initial conditions. And essentially all I'm saying to you is V Z of 0 does not equal to 0, and I Z of 0 does not equal to 0. Okay? Nothing not particularly exciting, because that's something that we usually experience in real life, but maybe a little bit more complex than what we had previously discussed. Now we'll go back to our analysis, and what we're going to remind ourselves of was that the voltage at any point along a transmission line is equal to the sum of the positive and the negative going waves. Right? We know that. And likewise, we know that the current is similarly, the total current is the positive and negative going current waves. And from our previous analysis, we had written a relationship between I plus and V plus in terms of Z naught, and I'm going to use this relationship and substitute this, you know, the positive and negative, you know, this relationship back into these two equations. And essentially, what I'm going to do is rewrite the difference in voltage in terms of, you know, the total current that's flowing on the line. And if you go through this, what you're able to do and do a little bit of algebra is convince yourself, my apologies, that the positive going wave is a half the Z naught 0 plus Z I naught of the total current, and the negative going wave is a half the total voltage minus the characteristic impedance on the line times the total current. Now you're going to say to me, Stan, well, super exciting, but who cares? And I'll say to you, well, you should care, because what we're going to do now is we're going to say, oh, let's assume, for argument's sake, that the voltage, we've got the following system. We've got a transmission line which is unterminated on both ends. It's got a characteristic impedance, but we had charged it at some time in the infinite past, and it's got a voltage current standing wave pattern on it. And at some stage in the future, I'm going to close this switch, and I want to work out what the voltage and current is on this, is going to be across this load. Now, for argument's sake, okay, let's assume that the voltage on this transmission line has the following spatial distribution, which is it's 50 volts from, you know, Z equals 0, or the distance Z equals 0, to L on 2, and then from L on 2 to the load, it diminishes or decreases as it goes from 50 to 0. And likewise, let's assume that the current has the following pattern. Now you might say to me, Stan, where did you get all this? You know, this is crazy, this is nuts, you're mad, all the compliments you can think of. This example is meaningful because it also relates to a dipole, right? So all of a sudden you can think of a situation where you're actually going to ground one of the ends of a dipole, and you want to know what's going to happen. But anyway, let's assume, let's forget about the practical, the reason from where this comes from, other than to say, hey, we've been told that this is the current and voltage distribution on this line. And from the equations here for the positive and negative going voltage waves, we can actually, given that we know V and I, and we know the characteristic impedance, we can actually calculate, and here I've written these graphs in terms of equations, and then all I've done here is actually worked out for you the impedance, the positive going voltage wave as a function of distance, and also the negative going voltage wave as a function of distance. Right? All I've done is I've substituted those equations into my equation for voltage and current as a function of V naught and I naught. So I'm trying to work out V plus and V minus in terms of I naught, V naught, and characteristic impedance. And once you do that, what you can actually convince yourselves, is that what you get after you do the appropriate substitution is this is the resulting voltage wave for the positive going the positive going voltage wave, and likewise this is the negative going voltage wave. So far all I've done is said, hey, I'm going to look at these. I've been given this transmission line. I've been given the voltage. We know that it's in steady state, but the only thing I can measure is I naught, V naught, right, as a function of Z. If I had a voltage meter and I didn't have a vector voltage meter, and essentially what I'm doing is using those relationships. I am showing you what the components are for the positive and the negative going voltage wave. Now, question. Suppose I connect to this system which I had. So let me find the graph again. So this system, let's connect. We know that this line is 50 ohms. Let's now connect a 50 ohm load to it. So it's going to be matched. So there's not going to be reflections, right? So I want to know, based on the current voltage on the line, in terms of the positive and negative going voltages, and I connect a load which has a characteristic, which has an impedance matched to the characteristic impedance of the line, what is the voltage that I'm going to expect and am going to see for this across this load? All right. So initially, once we connect the load, what we're going to have, and remember this is the positive going wave, and we said that the positive going wave is, I forgot what the distance was, it's 1 microsecond. So essentially what happens is we've got this signal, okay, is going to go through the load, right? So essentially what we're going to see initially is this signal is going to travel through the load, right? And then before we start getting this signal, which is going to be reflected, right? And it's going to be reflected from an open source, sorry, an open circuit, I should say. So it's just going to be, you know, the phase is going to change, so it's going to be, sorry, the voltage phase is not going to change, it's just going to be flipped in time. So essentially what we're going to do is we're going to get this, plus this component is going to be fed through the line, through the load. So this, essentially what we're going to see is this resulting voltage on the load as a function of time. Blank faces, I probably, okay. What I'll do is, let me go through, I'll put a couple more slides on in the next lecture. Okay, but essentially all I've done, there's nothing magic, all I've said is we've got this, our initial positive going voltage, right? So this initial positive going voltage is going to come through the load, right? So initially the load is connected here, right? So the load's initially going to see 0 volts, it's going to see nothing, it's going to see this, and this, until we get to this point. At this point, right, this has reflected, right, and has reached this point also. So essentially what you start seeing is this effect, right? Oh, sorry. So you start seeing this effect. So this has reflected, it's open circuit, so gamma is +1. So all of a sudden it's flipping, and so what you've got for this section, between these two, when they start arriving at the load, is you're going to start getting this joining up to this, and you're going to start seeing that segment through the load. That's all I'm saying. So all of a sudden you're going to get a different resulting pattern through the load, which is the combination of the positive going signal that was going through the load plus the signal that was reflected, came back to you, and then all of a sudden it's going to make itself make itself through the load, right? And that's what the load's going to see. Okay. All right. That's it for this lecture. Yes.
Can I make a suggestion? There's a professor in Canada called Professor Truman who's written a piece of software called Bounce, and you'll find it at the University of Concordia on their website, and it will show you